Now we're going to transition to potassium. So serum potassium is our primary intracellular cellular cation. So cation, remember, plus sign. Intracellular means uh, inside. So potassium is mostly on the inside of the cell. There's less potassium on the outside. And what I also want you to keep in mind for this is our action potentials. So that'll be our negative 55 millivolts. So recall that when we have an action potential, it's primarily started by the sodium, goes up, we have hyperpolarization, and then it evens back out. So this point right here is where potassium channels open. That's going to lead to the first repolarization. This is the hyperpolarization. And if you don't remember this, please open those Zoo 3115 notes back up. So potassium is important because it's going to help us maintain acid-base balance, fluid balance, but most importantly, nerve impulse transmission. So hyperkalemia can be a result of renal failure, severe injury like a burn or crushing injury, or decreased adrenal gland function. So this is going to be with aldosterone. Hypokalemia, on the other hand, is primarily due to diuretic use, vomiting, diarrhea. When you have vomiting, diarrhea, diuretic use, then it's usually associated with eating disorders, IV administration without potassium, and refeeding syndrome, which we'll get into in one moment. So urinary potassium is a marker of kidney function. 24-hour urine is reflective of the potassium ingested because a majority is excreted in urine. So this is why the diuretic use can lead to hypokalemia, because if we're using a diuretic, we're peeing more often, we're losing more potassium. And the potassium in the second void, or second P of the morning, is also correlated with potassium intake. So I mentioned refeeding syndrome. So over here, this is a beta cell. And beta cells, of course, secrete insulin. And they secrete insulin when they detect glucose. All right, keep that in mind. So we're starting here. We have our glucose, but this is a low glucose concentration scenario. And when we don't have a lot of glucose, it means we don't have as much ATP as ADP. Because remember, glucose gets turned into energy. For us, energy is ATP. So if we're low glucose, that means we have more ADP than ATP. And this signals for potassium channels to be open. This is our hyperpolarization. So again, remember that action potential. Probably thought, oh, I'm a nutrition major. Why would I ever need to know about nerve transmission? Well, this is why. Negative 55. So we'll say that it kind of creeps up, then it shoots, then hyperpolarizes, and then it. So again, this dip is the hyperpolarization. Oops, sorry. And this occurs because potassium channels are slow to close. So this cell is in a state of hyperpolarization. It can't excrete anything. It can't send a transmission because it's hyperpolarized. We have to reach above this threshold, which is usually negative 55 millivolts, for our action potential, because this part is the action. Okay, well then glucose increases. So we have more glucose, coming into the beta cell, goes to the mitochondria. The mitochondria turns glucose into ATP. And when we have more ATP than ADP, it closes the the potassium channel. Actually opens the calcium. And that's going to allow for insulin secretion. So when we have the ability to make an action potential, in this case, it's going to be for insulin secretion. We're all good. I'm going to clear these now. Okay, so let's look at a peripheral cell. The insulin that we secreted is going to signal for these peripheral cells to bring in glucose, as well as some phosphates and thiamine. When that glucose gets in the cell, we're going to do glycolysis and TCA cycle and ATP synthesis in the mitochondria. But in order for ATP synthesis, we have to have our potassium-sodium gradient, which means we need to pump sodium out of the cell and we need to pump potassium into the cell. The problem with this is if we refeed too much, too rapidly, we get a rapid increase in serum insulin. That's going to lead to a movement of extracellular potassium. So this potassium on the outside, this is extracellular, into the intracellular compartment. So all of this is going to move in. And that's going to lead to a dangerous decrease in potassium levels. So this is refeeding syndrome. And if we have this, if we don't have enough extracellular potassium, we don't have the correct concentration gradient, we are not going to be able to have our nerves function. We're not going to be able to run this NAK pump for very long. And so that is very dangerous. Now we're moving on to calcium. So when most people think of calcium, they think of bones, right? But the most important part of calcium is not bones. It's again related to action potentials, and specifically smooth and striated muscle contraction. So because muscle contraction is so important, think about tetanus. It's very important that our serum calcium be tightly controlled. And this means that our serum calcium is not related to diet or status. If we forget to drink milk for a couple of weeks, we can't just have our serum calcium plummet. We would die. That would not be evolutionarily advantageous. So calcium is stored in the bone, but this isn't its main role. Its main role, again, is this smooth muscle contraction and nerve impulse transmission. And we can have three types of calcium. We can have ionized. This is in the intracellular regulation. So this is our smooth, I'll just say striated muscle contraction. We have the protein-bound form. And this is approximately 40% of all serum calcium. So protein-bound means it is bound to something. What is it usually bound to? Albumin. When in doubt, it's usually, whatever it is usually bound to albumin. The remaining 20% is bound to other globulins, so other proteins. We want to make sure that our calcium, when it isn't actively being used in the ionized form, is bound, because otherwise we would have poor control over our muscle and nerve impulse transmission. So then 10% of total calcium is bound to small anions. This means it's complex. So this could be bicarbonate, phosphate, citrate, or lactate. That means it's something like calcium. It has its nice little cation. It finds an anion like, we'll just say bicarbonate. I'm just going to say bicarb, which has a negative. And then because negative and positive, they're going to form a salt. So they're going to be just like when we think of NaCl, that's another salt. So we will get the calcium bicarbonate. So altered calcium is rare, and it indicates a very, very serious metabolic problem. So hypercalcemia is related to hypoparathyroidism, renal disease, and acute pancreatitis. Hypercalcemia, pretty much the opposite, hyperparathyroidism, vitamin D toxicity, or hyperthyroidism. And so let's remind ourselves what the parathyroid gland has to do with this. So, we'll get there in 1 second. Let's talk about phosphorus really quick. So, phosphorus closely correlated with calcium. Hyperphosphatemia, so too much phosphate, is associated with hypoparathyroidism. Well, what was hypoparathyroidism associated with calcium? Hypokalemia. So it's negatively correlated with calcium, meaning if one goes up, we'll say calcium, phosphate should go down. Likewise, if phosphate was high, calcium should be low. We also see hyperphosphatemia with excess phosphorus intake, and you may be wondering, where do we even get phosphorus in the diet? We'll get to that in a second. Hypophosphatemia is associated with rickets, so think vitamin D. Osteomalacia, which is the grown-up version of rickets, also vitamin D. Chronic use of antacids containing aluminum hydroxide or calcium carbonate, because this will bind to phosphorus in the GI tract, and then we will essentially poop or pee out that phosphate. So we don't really think about phosphate a lot. Most of the time when we are talking about phosphate, it means that we're talking about like our teeth or something. Well, interestingly, a large source of phosphate in our diet is from sugar-sweetened beverages. Specifically, these non-carbonated, but like fruit-flavored ones are very high in phosphorus. So we only need around, if we're a guy, 3,400, if we're a gal, 2,600 milligrams of potassium. So if we are drinking a lot of Hawaiian Punch, and this is per 8 ounces, we may be getting way too much phosphorus. So let's think about, how much, we usually drink what, 20-ounce sugar-sweetened beverage? So 8 goes into 20, let's see, around 2.5 times. So that means we would multiply these by 2.5. So let's see what that brings us. Sorry, I'm not showing the calculator on screen, but I am using a calculator. That gives us 437.5 milligrams. So if we're a lady and our needs are around 2,600 divided by 437.5, that's about a sixth of our daily intake. So as you can probably imagine, People can drink multiple sugar-sweetened beverages per day. So if they were to drink about 5 sugar-sweetened beverages per day, which isn't unlikely, or um, think about if you get one of those like jumbo sizes, like at the movie theater, they're like 100 ounces or something. You may easily be reaching your daily potassium just through a sugar sweetened beverage. And this is a problem because if our potassium is high, it means our calcium is low. So this excess sugar sweetened beverages is going to be high phosphates, and that's going to lead to low calcium. That means that we're going to have to take calcium out of our bones to maintain our calcium balance, and that can lead to weakening bones. So, sugar sweetened beverages are bad for us for a variety of reasons, but people generally don't realize that, especially ones with high phosphorus, can be weakening our bones. Okay, now we're going to transition to markers of mineral status. So, the primary marker of mineral status that we will generally deal with in our day to day is anemia. So, anemia, characterized by the reduction of the number of erythrocytes, or red blood cells, per unit of blood volume. So, that's important. So maybe think about our unit of blood. We have enough red blood cells in it. It's fine. Then maybe this is a volume of 1. Volume equals 1. If we increase the volume, let's say this is volume equals 2, but we keep the same amount of red blood cells, 4, 5, 6, 7. This will be anemic, not because there's necessarily less blood cells. There's the equal amount of blood cells in these two boxes, but because the volume, and we'll call this box B and box A, there's simply less concentration of blood cells in box B. And so this is the type of anemia we see during pregnancy. Blood volume increases, but the red blood cells don't increase, so we're anemic because there's simply more volume. We can also get anemia if there's a decrease in hemoglobin in the red blood cell. So the red blood cell, this is a big red blood cell, has heme inside, and heme is what has iron bound, and that iron is going to bind oxygen or CO2. So if we don't have enough heme, we also are going to have anemia. And heme is what gives our blood cells their nice red color. So if we have low heme, we have pale blood. Low heme, pale blood cell. Red blood cell. So there's different types. We can have microcytic, meaning if this is a normal size blood cell. Microcytic means the blood cell is too small. Macrocytic means the blood cell is too big. And when it's too big, it's usually poorly formed. We can make this look kind of weird. So iron deficiency anemia is probably the most common. It's a microcytic, and it's because we have the heme, but it doesn't have the iron. We also can get vitamin deficiency anemias. Pernicious anemia is a condition in which B12 can't be absorbed in the gastrointestinal tract, and that leads to a malformation of the red blood cells. That's where we get B12 is usually associated with a macrocytic anemia. So the blood cells are big, They're poorly formed, they're usually more fragile, and they're often pale. We can get anemia just due to pregnancy if we're something or someone who can get pregnant, and that again is due to the volume. Aplastic anemia, this is due to bone marrow. Because all of our red blood cells are created in bone marrow. So if we have something like bone marrow cancer or radiation poisoning that has affected our bone marrow, we're not going to be able to make any red blood cells, and that is called aplastic anemia. There's nothing we can do about aplastic anemia as an RDN. We can ameliorate the symptoms, but there's no way that with diet or nutrition that we're going to be able to fix the bone marrow. Hemolytic anemia is due to red blood cells breaking. So for whatever reason, there's lots of reasons. This could be due to a virus, there's certain bacteria, toxins are going to cause hemolytic anemia. With hemolytic anemia, because these red blood cells are literally breaking, you'll often see some sort of bruising. Again, hemolytic anemia is usually not associated with diet unless it's because the blood cells are poorly formed and weak, and so they're breaking easier. And then finally, we have sickle cell anemia, and this is where the blood cell, instead of being our nice round shape, is literally sickle shaped, or kind of looks like a crescent. And because of this, it cannot hold as much oxygen, and it is going to cause anemia. Sickle cell anemia is a genetic disorder, but we can help ameliorate the symptoms with diet. And there's a lot of other anemias caused by other diseases and simply from bleeding out. This might seem obvious. Think about if you got stabbed or shot, you would get anemia because you're losing blood. But this can be more hidden. Say if you have a bleeding ulcer, you may present with anemia, but it's not from any of these reasons. It's because you're losing blood from a bleeding ulcer. So, laboratory tests for iron deficiency anemia. Of course, we can test for serum iron. That's kind of step one. But we can also look at total iron binding capacity. So, are we able to bind iron? Do we have a lot of iron binding capacity? That would mean we don't have enough iron to bind. We can look at transferrin saturation, so the amount of iron compared to total iron binding. So again, remember that like proteins have our binding sites. Normally, all these binding sites should have an iron associated with them. But if we don't have enough iron, then we're not going to be able to fill up all of these binding sites. So low total binding or increased capacity to bind, this has a higher binding capacity because it has these empty spots, means that we have less iron. We can also check for zinc, protoporphyrin, or erythrocyte protoporphyrin. So heme is made up with iron. When we don't have enough iron, heme will substitute other minerals that are similar, like zinc. But zinc does not bind oxygen as well. In fact, zinc is +2, but it doesn't have the capability to go to +3, so it's not as efficient. But this would indicate that we don't have enough iron as well. If we have decreased ferritin, so we're not storing as much, and increased soluble serum transferrin receptor test. So this is going to, again, test what is the binding capacity. So let's just have a little reminder about iron metabolism and physiology. First things first, we have two forms of iron. We have ferrous, which is the +2, oops, there we go. And we have ferric, +3. So in its +2, it's an electron donor. When it is ferric, it's an electron acceptor, because an electron is a -1. So if we have +2, it can give away 1 electron, it becomes ferric. When it adds an electron, we decrease +3 to +2, it moves from ferric to ferrous. Ferroportin is the iron transporter. So this is a protein, and we transport iron in the gut and elsewhere through ferroportin. So it can go from the mucosal cells into the blood through ferroportin. Ferritin is a protein again, and this is going to store iron and release iron as needed. So we want to have backup iron in case we need it, but we can't just have a bunch of iron free floating in our blood. So then we have a big, it's not big, but it's a protein, and it is going to store iron to it. Transferrin, another protein, is how we're going to transport our iron in the blood. So again, we don't want to just have electron donors and electron acceptors just kind of willy-nilly in the blood. So we need to attach it to a transport protein, transferrin, so that it can go to the tissue that it needs to and probably be incorporated into heme or some other tissue. So this is a fairly new hormone, but for a long time it was unclear how ferroportin was regulated. We knew it had to be regulated somehow, but we hadn't found the hormone yet. In the past 10 years, we found hepcidin. Hepcidin is the hormone that decreases ferroportin, and it comes from the liver, and it's going to regulate if this is available. Ferroportin is available. And so from there, we see that we have ferritin in the liver, we have it in the mucosal cells, we have it in the kidneys, and then we're going to use transferrin in the blood to transport the iron. And again, the iron can switch between its ferrous and ferric state. So let's also briefly look at how erythrocytes are formed. So we have a lot of precursors to erythrocytes. If you take the biochem3, I think, you have to memorize the pathway. You don't have to memorize the pathway here. But you do need to know that in order to make hemoglobin, we first start with a protein called protoporphyrin. And when we have protoporphyrin, two things can happen. If we have enough iron, and this is in the ferric state, we can incorporate the iron into the protoporphyrin. It'll be ferrous protoporphyrin, which we call heme. You add that heme to an even bigger protein, which is a globulin, and what do you know? You get hemoglobin. But when you don't have enough iron, the body then says, well, we need to make red blood cells, we need hemoglobin, we're going to have to use something similar, so we're going to use zinc. Again, 2 plus, 2 plus. The problem is zinc is not a good electron donor. So we get zinc protoporphyrin, and that protoporphyrin will become hemoglobin, but because it's not a good electron donor, it's not as effective as iron. So there's multiple markers of iron status, and there are models that combine several indicators of iron status, and these are better at distinguishing iron deficiency from other anemias, say caused by infection, inflammation, chronic disease. So a couple of the models are the body iron marker, and this is going to measure serum ferritin, soluble transferrin receptors. So we're looking at serum ferritin, so iron storage, soluble transferrin receptor. We're looking at the transport protein's ability to grab and bind iron. There's the ferritin model, where you look at serum ferritin, transferrin saturation. So here we're just looking at how soluble is the transferrin receptor. Here we're looking at how much iron is bound to the transferrin receptor. And we're looking at our EPP, which, if you recall, is our erythrocyte protoporphyrin. So how well are we making our red blood cells, making heme? And finally, we have the mean corpuscular volume model. So this is going to look at mean corpuscular volume, so how big is the blood cell, transferrin saturation, and how well we're making our heme molecules. So to get a better understanding of this, we can look at the stages of iron depletion, because what these different models are going to show us, as well as just kind of basic, do you have iron deficiency anemia? It's also important to know how severe it is, what stage of iron deficiency anemia are we at. So if we have tissue depletion, so we don't have enough iron, so we're going to use the iron from the tissues, we're going to see a decrease in serum ferritin, because remember, this is the storage. So this is basically like if you've ever worked in a restaurant or something, someone asks for something, you go to the back, there's none left. We don't even have any in storage. We have tissue depletion. We can also look at functional deficiency, but without anemia. So you might have tissue depletion, you don't have anything in storage, but you don't have anemia yet, because you're able to keep making your blood cells. The blood cells look normal, but if you're basically on the edge of becoming anemic. So this is a functional deficiency without anemia. You're going to see a decreased transferrin saturation, so less iron being transported. You're going to see more of the precursors to heme, because it's not being made completely. And you're going to see increased serum transferrin receptor. So receptors are available and not being used. Next, we have just full-blown anemia. So we've depleted our storages, right? At functional deficiency without anemia, everything's still working, but we're not transporting as much iron. We have more precursors available, and receptors are available. And we're not going to be able to go to our storage because we already have tissue depletion. So now we have anemia. This is going to be marked as a decrease in hemoglobin. Sorry, that's spelled wrong. There we go. And we're going to see a decrease in hematocrit. We're going to see decreased mean corpuscular volume, which means small red blood cells. So when we're looking at our red blood cells, we usually get a red blood cell count. And we can look at the mean cell volume. So again, we could have them be too small, normal, or too big, poorly formed. So this measure is called RDW-CB. It's the red blood cell distribution width. And it's measured by calculating the width at 20% the height of the red blood cell distribution, which is this histogram. Oops. Let me take those off really quick. So we have all of these red blood cells, and we want to see what the frequency of each size is. So usually the frequency, this is the mean. It's the most common size. So we have some cells that can be big, and we have some cells that are small. We mostly want, though, our cells to be around the mean. So if we have a really, really wide red blood cells width distribution, it means we have a bunch of small red blood cells and we have a bunch of big red blood cells. If the mean itself is shifted, that means that we're able to say, okay, this is either macrocytic or microcytic. So the mean is going to give us macro or micro. The width of the curve is going to tell us, even if the mean is normal, do we have a bunch of cells that are not around the mean? So we have a large distribution of different cell types, cell sizes. Okay, let me erase this so that when I do put these boxes back on. So changes in either the width of this curve or the mean corpuscular volume. So this is the mean corpuscular volume, is going to influence a red blood cell distribution width. If we have a microcytosis, small cells, it's going to reduce the denominator of this because this is going to be small. In macrocytes, this is going to be big. So if we have microcytic anemia and the denominator is small, that means this is going to be bigger, and that's going to mean the distribution is big. If we have macrocytic, that means that this is going to be a big number. If you divide something by a big number, you're going to get a small number. That means the red blood cell distribution is going to be small. So now moving on to zinc status. So zinc is really important for protein synthesis, wound healing, immune function, growth, and taste. So we don't have a sensitive biochemical or functional indicator of zinc status. And that's because zinc is in a lot of tissues and it's highly conserved. The other problem is zinc is so important that it's maintained. Serum zinc is maintained at the expense of tissue zinc. So serum zinc is not reflective of changes in dietary zinc and is only a late indicator of zinc pools. So if serum zinc is already low, that means tissue zinc is very, very, very low. We do see a decrease in serum zinc in stress, inflammation, infection, with estrogen use, corticosteroids, and it can be altered by meals. But this infection, inflammation, this is why you see like cold medicine has zinc in it. So some alternative zinc indicators are metallothionein, which binds zinc and copper, and it's found in most tissues, or urinary zinc from a 24-hour urine collection. But overall, zinc is difficult to measure. For calcium, like I mentioned, serum calcium is tightly controlled and not related to diet status. Urinary calcium is somewhat responsive to changes in dietary calcium. More is excreted when serum calcium is high, but that's dependent on our other electrolytes, like sodium, but as also protein, phosphorus, the urine volume, and kidney function. It also shows a diurnal variation. It can be higher in the day and lower in the evening. But calcium from overnight urine is an indicator of compliance with calcium supplement. But it's important that it's overnight because of this diurnal variation. There's no appropriate indicator of calcium status. What about phosphorus level? The phosphorus level is closely correlated. Remember that it's negatively correlated with calcium. We see higher phosphorus with dietary phosphorus intake, like sugar-sweetened beverages, and use of phosphate-containing enemas and laxatives. However, it's not reflective of phosphorus status. Again, phosphorus is pretty important. Think about ATP. What does the P stand for? So hyperphosphatemia is usually seen in renal failure and with high dietary phosphorus. Hypophosphatemia is usually related to vitamin D, like rickets and osteomalacia. So let's think about vitamin D status. So we don't have a good marker of calcium or phosphorus, really. And unfortunately, we don't have a great marker of vitamin D. We have an okay marker. We have 25 OHD concentration. So the problem, though, is that 25 OHD, vitamin D, this is not the active form. It is influenced by the active form, but also by parathyroid hormone, serum calcium, and phosphorus. It has a short half-life, which is good because that's going to tell us, that's going to be more accurate on the day by day. The biggest problem, though, is that sun exposure has the largest effect. Dietary vitamin D and vitamin D status are very rarely correlated. And body size and adiposity influences serum vitamin D status. Adiposity because vitamin D is a fat-soluble hormone or fat-soluble vitamin. But parathyroid hormone can tell us more about vitamin D. So just as a reminder, how we get our vitamin D to the active form. So we start with cholesterol. It is then transformed into cholecalciferol, vitamin D3, again, not active. And it is because of sunlight. We have a vitamin D pool in the liver. The liver then takes this from D3 into 25-OHD. That will then be our circulating form. But our actual active form, which is important in the kidneys for calcium retention, is very hard to measure. Most people don't want you poking their kidneys, and so we can only measure this inactive circulating form. We can't really measure the active form, which is responsible for the calcium retention. But parathyroid hormone, which we can measure more easily, is what causes the conversion to the active form. So we can infer the active form based on our parathyroid hormone secretion. So when we have low plasma calcium, that's going to signal to the parathyroid hormone to secrete. That's going to change our inactive vitamin D into the active form and increase calcium retention. It's also going to increase calcium absorption from the mucosa, and that's going to lead to higher plasma calcium. So, iodine status. Iodine, we can measure urinary iodine, we can look at thyroid stimulating hormone, and we can look at serum thyroglobulin. So urinary iodine is the most widely used indicator of recent iodine intake and nutritional status. Spot urine is acceptable for populations, but not individuals. So this is like a research value. Most of our iodine, about 90%, is eventually excreted in the urine, so urine will tell us about how much we've consumed. But it can be affected by hydration status and day-to-day differences in intake. So just as a reminder why iodine is related to TSH and thyroglobulin is because when we're making thyroid hormone, so here's our thyroglobulin, we need iodine from the blood. Iodine is taken into the thyroid gland through a sodium symporter, so we also need enough sodium. From there, the iodine is then put onto our thyroglobulin. It gets conjugated, goes through some fancy things. And we get two types. We get thyroxine and we get triiodothyronine. And these are our two forms of thyroid hormone. And you can tell the little purple color is the iodine. The difference between the two is how many iodines are on it, 3 or 4. So thyroxine is the active form, triiodothyronine is the less active. Oh, excuse me. thyroxine is less active. I misspoke. Triiodothyronine is the active. And because thyroid hormone is just that, a hormone, it is regulated by the hypothalamus. This is thyroid releasing hormone. TRH is not circulated. This is only found in between the brain and the pituitary gland. From the pituitary gland, though, thyroid releasing hormone will promote the release of thyroid stimulating hormone. This is circulated, so this one's not. This one you can find circulating. And thyroid stimulating hormone is released from the pituitary gland onto the thyroid, and it stimulates release of both T4 and T3. Active, inactive. Because this is an inhibitory feedback system, T4 and T3 act on the pituitary and will decrease the stimulation of TSH, and they'll also do inhibitory feedback at the level of the hypothalamus and decrease TRH. So if we have high T4, we should see decreased TSH and decreased TRH. We almost never measure TRH. It's too difficult to measure in humans. So mostly we measure TSH and T4. High T3 also should be related to low TSH. So now let's move into vitamin status. There's a lot of vitamins. We have functional and static assays. But especially with B vitamins, we're going to need functional assays. And some deficiencies we expect together. So things like thiamine, niacin, riboflavin, and B6 tend to be together. B12 and folate, as well as folate and vitamin C. So let's start with thiamine. Thiamine, we're going to need a functional assay. So we're going to have to measure erythrocyte transketolase activity coefficient. Remember, erythrocyte is a red blood cell. So erythrocyte transketolase is a thiamine-dependent enzyme. And so ETKAC is determined by measuring the basal activity of the enzyme with and without added thiamine. Thiamine is the coenzyme. The problems with this, and honestly with most functional assays, is it's expensive. We can measure thiamine in the urine and the blood. In the urine, not really. Not a great measure. Thiamine in the urine is reflective of recent dietary intake, but not status. So let's just remember where we find a transketolase. So in glycolysis, remember we get glucose, comes into the cell, we put a phosphate on it. This is hexokinase. We get glucose, we're going to turn it into glyceraldehyde 3-phosphate. So we've added some phosphates. There's several enzymes in this. And then eventually we're going to go down to pyruvate. Pyruvate can either stay as pyruvate or it can become lactate through lactate dehydrogenase. If it goes through pyruvate dehydrogenase, which needs thiamine, it'll become acetyl-CoA, and then we're in the TCA cycle. And then we have alpha-ketoglutarate down here as we go around, and it will become succinyl-CoA through an alpha-ketoglutarate dehydrogenase, which again needs thiamine. A lot of dehydrogenases need thiamine. We also have a transketolase that needs thiamine, and this is important in the pentose phosphate cycle. So if we don't have enough thiamine, we can't metabolize glucose. This is important. This is where when people say B vitamins give you energy, not really. But they're important for utilizing energy for glucose. So think about where thiamine, which is TPP, is necessary. If you don't have enough thiamine, what metabolites will be increased? What will be decreased? What will be the effect on nitrogen balance? So moving right along, next B vitamin, niacin. So we don't have a functional assessment for niacin. We have to rely on blood concentrations or urine end products like N-methyl nicotinamide and N-methyl-2-pyridone 5-carboxylic amide, or 2-pyridone. So the premise behind this is that 20 to 30% of niacin is excreted as N-methyl nicotinamide, and around 40 to 60 as 2-pyridone. So both markers decrease with niacin deficiency. So if we have less urine by end products, we probably have less niacin in general. The low NMN is more sensitive and easier to measure clinically. This 2-pyridone may decrease to 0 before clinical signs begin to appear. So NMN is the preferred marker. Just a reminder about niacin and nicotinamide. So we get it from our diet, right? So we can get just niacin. It becomes nicotinamide, or nicotinamide can become niacin itself. So we may get niacin from the diet. We may get nicotinamide. It's going to become niacin eventually. This niacin eventually is going to become NAD. Think about where we need NAD. Why is NAD important? We can also generate a certain amount of niacin through tryptophan, but not enough. That's why it's a vitamin still. We still need to consume niacin. So nicotinamide is important for our redox reactions. So glycolysis, TCA cycle, and oxphos. We also need it for DNA repair. All right, next one, riboflavin. So for riboflavin, we have a functional assay, erythrocyte glutathione reductase activity coefficient, but we can also look at urinary riboflavin excretion. But we have to correct for gram of creatine. So erythrocyte glutathione reductase is an FAD-dependent enzyme. Think about what FAD is. FAD. So if erythrocyte glutathione needs FAD, it needs riboflavin. I always remember it because flavin, FAD. So this is a newer assay. So really the problem is that we just need more information. But to remind yourself where we see glutathione, we see it with the transition from hydrogen peroxide to water. So this is important in oxphos. It also requires selenium. But this glutathione reductase, which is going to take NADPH to NAD+, requires riboflavin, or FAD. So GSH is an antioxidant, but its function requires FAD. We also can look at the folate methionine cycle. So remember that folate is a B vitamin as well, it's B9. And folate is important for the SAM-SAW cycle. And what it's doing here, so we get folate, tetrahydrofolate. It's going to take a serine and make it a glycine. We also need B6, and we also need B12. And what this is interacting with is the methionine cycle. And this is taking homocysteine and recycling it into methionine. This is particularly important because we need this for DNA repair. So B6, B12, and folate are critical for one carbon metabolism, meaning we're taking one carbon, or a methyl group, so any disruptions to one carbon metabolism are going to result in anemias and DNA replication errors. When we get DNA replication errors, we get cancer. So B6, we measure B6 using plasma pyridoxal 5-phosphate, or PLP. Fasting PLP is the most widely used and informative indicator of B6 status for healthy persons because PLP makes up about 90% of the B6 in our plasma. And in fact, if you're taking biochem, they'll usually refer to B6 as PLP. But the results can be affected by several diseases such as asthma, cardiovascular disease, and pregnancy, as well as by protein intake, physical activity, age, and blood glucose concentration. So we have a couple of other indicators. We have urine for pyridoxic acid, which is a metabolite, and we can also do the methionine load test. Urinary for pyridoxic acid is the major urinary metabolite of B6 and a useful indicator of immediate dietary intake. The methionine load test is going to look at, because we need PLP for the metabolism of methionine, those with impaired vitamin B6 have higher cystathionine and cysteine sulfonic acid after the consumption of methionine. They're unable to complete that cycle, but this requires a 24-hour sample and is not very common. So for folate, we can look at folate, sometimes called folacin, that's kind of old, or folic acid. So we can look at serum and erythrocyte folate. So this is, again, red blood cells. We can look at mean corpuscular volume and homocysteine. Serum folate concentration is an index of recent folate intake, whereas erythrocyte folate concentration is considered the best clinical index of depleted tissue stores. So this is serum, means that it's in the blood. Erythrocyte is in the red blood cell. So erythrocyte folate concentration is reflective of liver stores and total body status. And that's going to regulate the folate status at the time of red blood cell synthesis. The problems with serum folate are they can be affected by renal failure, liver disease, red blood cell hemolysis, oral contraceptive use, smoking, and alcohol intake. The other problem is we also see high mean corpuscular volume and homocysteine to be elevated in B12 deficiency. So how can you tell the difference? Well, for B12, we can look at serum or plasma total cobalamin, which is B12. We can look at serum holotranscobalamin, total homocysteine, or urinary or serum methylmalonic acid. There's no gold standard. We actually need several tests to determine B12 status. And the problems occur because MMA and total homocysteine are influences by changes in renal function. Also, they're influenced by folate status. So why might serum cobalamin be misleading when assessing vitamin B12 deficiency? Think about how vitamin B12 is activated. We consume vitamin B12 and it's absorbed, but we need intrinsic factor. And this comes from the parietal cells of the stomach. Intrinsic factor is going to complex with vitamin B12, and that is going to allow it to be absorbed in the intestine, specifically in the terminal part of the ileum, into portal circulation to be stored in the liver. We store quite a bit of vitamin B12 in the liver, and we release it into circulation as needed.